So welcome everyone for this new SIPTA seminars so this November SIPTA seminars. For those of you that are new to the seminar, the idea is to have each month a seminar about a topic related to IP, either from core IP people or people that are connected to IP. I would say in this case, it would be fair to say that Kevin is a core IP person, so he has done many contributions that are within the core of IP, and in particular, this one that he will present us today. Without further ado, as you know, usually we want the seminars to be shared by persons that know the topic as well as usually the person quite well. So today, Arthur Van Kamp, that knows Kevin quite well, accepted to introduce and chair Kevin's seminar. So without further ado, Arthur, I let you introduce in much more detail, Kevin.
Thank you, Sébastien. Good afternoon, good morning, wherever you are. Welcome to the SIPTA Seminar. I am Arthur van Kamp from the Eindhoven University of Technology, and it's my great pleasure to introduce Kevin Blackwell. Kevin obtained his PhD from the University of Michigan at Ann Arbor under the supervision of Jim Joyce. Kevin then moved to Bristol, where he started as a postdoc at the same time as me in the ERC-funded project Epistemic Utility for Imprecise Probability, EPIM for short, led by Jason Connick at the University of Bristol. And I had the pleasure of sharing an office with Kevin, and he has become a dear friend since. Kevin is now a lecturer in philosophy at the University of Bristol. Many of you know him well, for example, from his service as a member of the Poster Prize jury at the latest SIPTA in Bielefeld, but also as a co-organizer of the 2022 SIPTA Summer School and a co-organizer of various EPIMP events. It's obvious, and Seb already said so, Kevin is a core IP person, but he comes from the philosophy side of imprecise probabilities. So he is a living example of the efforts of Teddy Seidenfeld, Gert Koolman, Jason Connick, and others, of having closer interaction between the philosophy side and the SIPTA side, for lack of a better name, both sides of imprecise probabilities. One thing that you might not know about Kevin is that Kevin is incredibly curious about almost everything philosophy has to offer. He has, or so I like to think, a proper philosophy beast in him. He has an eagerness to develop sharp intuitions, insights about virtually any question that crosses his path, and he is very opinionated about them. He's also a wonderful conversational partner, as I have experienced many times myself, and I've learned a great deal of philosophy from Kevin. Kevin's research focuses on formal epistemology, decision theory, and imprecise probabilities. He has published about choice functions and set of reliable gamble sets, but also about sets of desirable gambles. And in his work, he has pointed out several surprising features in them, and which will be relevant to many of us. Therefore, I believe that the current seminar of today will be very interesting to our community. Please join me in giving Kevin a warm welcome.
Well, thank you so much, Arthur. And yeah, thank you all of you for being here for my talk. Cool. So before I sort of get going properly, let me say a little bit about what the topic that I'm going to be talking about today is. So the idea is suppose that we want to use a formal model to represent the choice or decision behavior or beliefs of an agent. So for instance, if we want to use sets of desirable gambles, then we're going to define a gamble as this function from omega to the real numbers. And we're going to say that g of little omega represents a reward or loss that the agent will get if that outcome in omega occurs. But, what is this big omega, right? Well, so it's supposed to be an outcome space, so mutually exclusive and jointly exhaustive. And intuitively, right, it's supposed to represent all of the outcomes that an agent is thinking of as possible. Now, of course, this isn't just a question for sets of desirable gambles. You have sort of the same question if you're thinking about a probability function or a creedal set, a set of probability functions. You have similar questions, right, if you're thinking about upper and lower provisions, right? So if you're thinking about what is the outcome space that the random variables are defined on, whatever. But so I am going to focus on desirable gambles for some reasons that might become clear throughout the talk. There are a couple of sort of natural questions that this raises. The first one is like, what happens if omega isn't really the agent's set of possible outcomes? And the other question is like, what happens if the agent changes their mind about what outcomes that they think are possible? And I think these questions are interrelated. So what happens if omega isn't really the agent's set of possible outcomes? Then what I'm going to be interested in is sort of two things. How do we translate desirability judgments from whatever the agent's actual outcome space is to how we're representing it? And like what's rationally required of an agent's desirability judgments under such a translation? For the second question, right, this is the phenomenon that I'm going to call awareness change. Okay, so here's the plan for the talk. I'm going to identify some basic kinds of awareness change. I'm going to formally characterize these kinds and use examples to motivate a translation scheme. Then I'm going to talk about coherence, both kind of right for the space of outcomes, they're like home space that an agent actually endorses, and on some other space, right, that might not be what they think are sort of the actual possibilities. I'm going to make kind of a minor, but I hope somewhat interesting connection with some ways that we think about conditionalization for sets of desirable gambles. And then I'll just sketch, like what my proposal for awareness change is. And then the very last thing that I'll do is I'll just mention some things that I have worked on that I'm not going to be talking about today in the talk, because I think this is going to be enough to try to get through. Okay, so let's talk about what awareness change is supposed to be. So it seems like intuitively, here are two basic ways that an agent could change their mind about what outcomes they think are possible, or four, if we want to say that there are kind of two directions of each of these ways of thinking about it. So you could have expansion, which is where the agent learns that there are some possibilities that they haven't accounted for like at all. Contraction, which is just the opposite of that, right? So there are some outcomes that the agent took to be possible that now they don't think are possible. Refinement, which is going to be when an agent learns that some possibilities that they were considering can be kind of broken down into some more fine-grained possibilities. Coarsening, right, is like the reverse of that. The agent learns that some possibilities they were considering aren't really distinct, or they stop treating them as distinct, we might think. In the philosophical literature on this topic, people usually call it awareness growth. And here, people are normally interested mostly in expansion and refinement, but not really talking so much about coarsening or contraction. I'm going to kind of talk about these as, just kind of versions of the same process, sort of. There are also other kinds of interesting translations between outcome spaces that I won't be considering for this purpose. So think about like if you have colors, words for colors in two different languages or cultures. So you might have, right, that these two languages are sort of, splitting up like the bands of colors, like the spectrum of colors in radically different ways. But like there's not any color that either is missing. Like every color kind of, gets uniquely mapped to like some color word. Um, and no possibility for one is strictly more fine-grained or coarser than the other. So you can have like kind of like the, different color words are kind of overlapping in some kind of complicated way. But you can't really just say, okay, like this thing is more specific and this thing is narrower or something, right? So I think that's really cool and interesting. And I'll say a little bit at the end that it's just to say that I think that this is a really hard question about how to think about this. But one thing is that, right, what I'm interested in this talk is sort of specifically gaining or losing expressive power. So I really am kind of interested in the case of where like I can make more judgments before or like fewer. And this case is not a case like that exactly. So it's super cool, but that's not what this is about. So I need to kind of do some like throat clearing about like an assumption that I'm going to be making in the background of this talk. When I define awareness change, I'm going to appeal to this like objective, actually disjoint and actually exhaustive and mutually exclusive set of possibilities omega. And it would be really convenient to think that there is a maximally fine-grained such omega that we can always appeal to. And philosophers often talk as if there is. We talk about like the set of all possible worlds or something. It's not super clear that this makes sense, right? Alan Hayek has a really good talk about this that you can watch on YouTube called Omega. I'm not going to talk about like all of the problems here, but I mean, one thing that you might think is like if there was such a collection, it would be like a proper class, not like a set. And so then like a lot of like set theory things that you want to do like aren't going to work. There are other things to worry about, like whether this makes sense. Right. Okay. So we don't actually need that this thing really exists for almost anything that I'm going to say in the talk to make sense. But it's really tedious to try to formulate what I want to say without it. So I'm going to talk like as if this is true. We can treat it as just like we're sort of pretending because it simplifies a bunch of things. It gives us a really nice way of talking about how these different things are related. We can kind of paraphrase all of this without assuming this, but I don't want to do that. Okay. So let's start with a definition. I'm going to say that delta is a partial partition of omega if one, every element of delta is a non-empty subset of omega, and two, any two distinct elements of delta are disjoint. So equivalently, right, just delta is a pairwise disjoint family of non-empty subsets of omega. We're going to take the outcome spaces our agents are working with to be partial partitions of omega. And what's really convenient about this is it gives us a way to interdefine any possibility our agents can consider, right? So this is a perspective where I can say exactly here's when these agents are talking about like the same thing, even though they're sort of carving things up in different ways. But of course, right, since this is, we're not requiring that it's a partition, like it's not exhaustive necessarily of omega. So agents can omit possibilities. Agents can lump possibilities together that other agents distinguish. And also, right, we're not really committed to the idea that every possibility in omega is possible in whatever sense we think is relevant to decision making. So we can definitely accept that agents are correct to reject possibilities in omega. We don't need to say that these are real. It's just sort of a useful way of being able to sort of talk about kind of what's different about these different things. So for instance, like let's say you thought that like the relevant notion is epistemic possibility, right? We don't need to say that all of these are epistemically possible or whatever. Okay. I'm going to say that a pure expansion is when an agent who takes partial partition delta to be their outcome space adopts partial partition gamma as a new outcome space, where gamma is a superset inclusive of delta. This allows maintaining the same outcome space as a degenerate case of expansion. For the non-degenerate case, this is to say exactly that the agent adds at least one possibility, which is disjoint from all of the possibilities that they were considering before. And so intuitively, right, this is exactly what we wanted to say. They're considering some new possibilities, which before they sort of weren't representing like at all. Pure contraction is just going to be the reverse of pure expansion in the obvious way, right? So they're moving to a smaller outcome space. So let's give an example of this. So think about Milo and the one-armed bandit. So Milo is in a casino, considering whether to play a slot machine. We can think of a play on the slot machine as a gamble. There are various possible configurations of the machine, and depending on which configuration the machine is in, pulling the lever is going to result in certain payouts. So whatever Milo's beliefs about how profitable the machine is, we can represent this as a set of desirable gambles defined on delta, where delta is going to represent all configurations that Milo thinks are possible. And of course, L of delta is the set of all gambles from delta to the reals. Unbeknownst to Milo, the machine in question will sometimes award a jackpot as a malfunction. What do Milo's beliefs look like to someone who knows that the machine can malfunction? And how should Milo change his beliefs if he came to learn that this can happen? Okay, well, call the malfunction state M. From the perspective of someone who thinks that delta union set M is the outcome space, it looks like Milo is completely ignoring what happens for M in any gamble. So it appears that if you sort of take the gamble that's like called off, right, like whenever M happens, um, and just that gamble, those are interchangeable for Milo. That's what this looks like. And this seems potentially really bad. The malfunction could, as far as Milo knows, result in arbitrary gains or losses. So like it could electrocute him as easily as give him a jackpot, right? He has no idea about like any of this. And of course, also, right, another thing to say is that Milo is going to be incoherent on this larger outcome space. Because in particular, he's not going to know to accept weakly positive gambles, which are strictly positive only on M, right? So what I'm going to say is that Milo is possibility blind to M, and I'm going to make this precise in a moment. So given any set of gambles D defined on delta, we can define the possibility blind equivalent set of gambles on gamma, which is a superset of delta, as blind gamma of D is just going to be all of the gambles that like take what it says about delta. And so gamma says, right, the gamble defined on gamma says all of those same things. And then of course, right, it can do anything for the things that, the gambles defined on delta don't say what they do. So another way of saying this, right, is that for any gamble defined on gamma, G is in this like blind possibility blind equivalent of D, if and only if the gamble, right, that's called off whenever something isn't in delta is also in that thing. Yet another way, right, of sort of repeating the point, if Milo judges that a gamble is desirable based on delta, right, he sort of only has to look at delta to figure out whether he thinks this gamble is good. And anything can happen on M, and that makes no difference to Milo, no matter what. So this possibility blind equivalent is the direct translation of D into gambles defined on gamma. Like D itself, it treats any gamma that's not in delta, so it's in gamma but not in delta, as having probability 0. More than that, it treats any such gamma as impossible in a sense that I'll explain in a bit. All right, so suppose that Milo learns merely that M is possible without learning anything about how likely it is. One sensible thought is that Milo should be radically uncertain about how likely M is compared to delta. So you might think like maybe he should maintain his beliefs conditional on delta, and he should do something like take the marginal extension with some kind of extreme ignorance on delta versus M. So it's not that I don't, think that there might be a reason to think that you should do this sometimes, right? I do think that could be plausible. But in a lot of other cases, right, like the way that Milo like sort of learns that M is possible, like suppose someone says, like I saw the machine malfunction once or something, right? And that might give Milo more evidence about how likely it is, right? So just this kind of radically uninformative thing won't be what he should think, right? It's going to place like some bounds on, maybe what the probability should be. Um, and basically, what I want to say in general is that there's not like a general story about what you should say, about what Milo's final belief should be here. These kinds of changes are going to involve highly substantive revisions of Milo's beliefs, which should be motivated by things like, what evidence he has, his attitudes towards epistemic and practical risk. Maybe you're kind of thinking like, oh, should I go like kind of vacuous, or, maybe I want to be able to sort of do inductive learning. So maybe I should have like an imprecise Dirichlet or something, like whatever, right? There are going to be all kinds of considerations here. And I'm not trying to like answer all of that right now, right? What I'm going to do is propose a minimal, maximally conservative change that respects Milo's previous commitments as much as possible, but involves coming to treat M as a genuine possibility. And so I think this is what reflects merely learning an outcome as possible. So if he still had good reason before, right, to treat it as probability 0 in the sense that he thought that the things in delta were like probability 1, sort of let's assume, unless we have some other specific reason, right, to think that that's still true. So that's what I'm taking to sort of be like merely learning that something is possible. More on that in a bit. For right now, let's talk about the other kind of thing, pure refinement or coarsening. So I'm going to say that a pure refinement occurs when an agent who takes partial partition delta to be their outcome space adopts partial partition gamma as a new outcome space, where for each gamma and gamma, there's unique delta and delta, with gamma a subset of delta inclusive. And for each delta and delta, the union of all gammas that are those subsets is just exactly delta, right? So what this says, right, is that, well, for one thing, like for expansion, we allow keeping the same space as a degenerate case. Delta and gamma are going to cover the same subset of omega, possibly its entirety. And intuitively, the agent isn't representing any entirely new possibilities, right? In the non-degenerate case, what's going on is that there's some possibility delta, and we've kind of taken, right, ways of carving up delta that combine to delta. And so we're just breaking down some possibility into some like finer components. And yeah, pure coarsening is just going to be the reverse of pure refinement in the obvious way, right? So let's give an example of this. Gray is colorblind. They can't distinguish red and green. Gray knows that a bag contains 3 coins. One coin is blue, while the others both appear to be gray. Gray doesn't know yet that they're colorblind and is actually unaware of the possibility that someone else may be able to distinguish these coins. So he just thinks, they just think like, yeah, these are the colors. Iris can distinguish red and green. Watching Gray, she sees that one of the non-blue coins is red and the other is green. Both Gray and Iris are considering gambles on the color of the coin that would be drawn from the bag. So let's say that Gray's outcome space is delta is just blue or not blue. Iris's outcome space is blue, red, or green. And suppose, for no particular reason, Gray has precise probabilities that, the blue coin is 1/3 and, not blue is 2/3. So then Gray's set of desirable gambles is just gambles where, G of B plus twice not, that G of not B is greater than 0. What does this look like to Iris, though? Well, to Iris, it's going to sort of look like Gray is precise on B versus not B, but maximally imprecise on how red and green contribute to not B. It looks to Iris that Gray only accepts gambles that have equal payouts on red and green. So like Gray is willing to accept the gamble -1 if B, 1.5 if not B, which Iris can see as the gamble -1, 1.5, 1.5 in her space, right? But Gray can't even conceive of the possibility of gambles like -1, 1.52. That's not a thing that Gray can represent. So, right, like that's not going to be desirable. And from Iris's perspective, of course, this looks irrational, like G dominates F. What do you mean? Like F is desirable, but G isn't, right? And it also, of course, is going to look like Gray is going to fail to accept some positive gambles, in particular, the indicators for red and the indicator for green, right? These aren't things that Gray knows what they are. So let's define this cylindrical extension for pure refinement. So consider any partial partition delta and any partial partition gamma, which is a pure refinement of delta, as I defined before. Given any gamble G defined on delta, we let its cylindrical extension G star, which is a gamble on gamma, be defined by, for all gamma and gamma, G star of gamma is just G of delta of gamma, where delta of gamma is the unique element of delta such that gamma is a subset of delta gamma. Remember, right, like when we defined what a pure refinement is, like that's going to happen. Similarly, of course, given any set of gambles defined on delta, we can take the cylindrical extension of all of those gambles and then just say that's the cylindrical extension of the set. Okay. So if we think about a set of desirable gambles, D star gamma, that's exactly the direct translation of desirability judgments on delta, this like D originally. Note that as we saw for Gray, right, if we have some gammas, which are kind of more fine-grained versions of a delta, then the cylindrical extension is sort of going to only accept gambles which are constant, over all of these gammas that are sort of refinements of this one delta, because making any distinction here would amount to being able to tell that these more fine-grained possibilities are distinct, which, like, by hypothesis, D defined on delta, like, obviously can't do. So, right, it's going to look like, right, when we translate in this way, that D is going to look incoherent when moved to this other outcome space. And of course, now we can put what we've said for pure expansion and what we've said for pure refinement together. So consider outcome spaces delta and gamma, where there's some outcome space lambda, such that lambda is a pure refinement of delta, and gamma is a superset inclusive of lambda. So gamma is a pure expansion of lambda. Then the translation of an assessment D onto gamma is going to be the possibility blind equivalent to gamma of the cylindrical extension of D to lambda, right? So we can just sort of chain those together. And this is part of why we wanted to allow degenerate cases of expansion and refinement, because now we can represent pure cases as special cases of this general scheme. And we can use this scheme for sort of two purposes. So we can model an agent's judgments on an outcome space that isn't their own. So we can say, okay, what is Iris going to say, you know, about like what Gray is doing? We can say that kind of stuff. But we might also sometimes be interested in the agent actually moving to the new space. So yeah, with representing their prior beliefs as the first space of this process of moving. So what we should think about coherence in these two cases is going to be quite different. So let's talk about the sort of standard coherence axioms for sets of desirable gambles and what this says about the possibilities that an agent is considering. So we have our standard coherence axioms, right? So we have that the zero gamble isn't desirable, the positive gambles are, we have addition, and we have positive scaling. But question, what's the best justification for this positivity axiom? Well, I think, right, it's a weak dominance argument. So the normal thought is, if I think every outcome in delta is possible, then any positive gamble represents partial gain. Because what this says is I can't lose utility in any outcome, and there's at least one where I gain. And so as long as I think every outcome is possible, right, then this is surely an improvement over zero. Like I can't do any worse, and like I might do better. And of course, right, this is supposed to be true no matter how unlikely the outcomes where I gain are. It's supposed to be about mere possibility. So in particular, I could think that an outcome has probability 0, but I could still think that it's possible. And then, right, this sort of weak dominance argument is still supposed to apply. But of course, that raises the question of like, well, what if I don't think delta is possible? Then there seems to be no reason that I should be irrationally required to prefer the indicator of delta to 0. In fact, right, sort of standard way of defining conditionalization for sets of desirable gambles relies on exactly this idea. So take like the kind of hook version of conditioning, right? So we restrict to the gambles defined only on E, and it's the indicator of E of F. If that's in D, right, then now F is in this updated thing. So when I become certain that event E obtains, I treat all outcomes inconsistent with E as completely irrelevant. And in fact, what I'm going to claim is that I'm now treating them as impossible, right? Like I threw them out of my space, even in this version of conditionalization. So suggestion, an agent is required to find the indicator of some event E desirable if and only if that they think that that event is possible. And what this means is that if we think that an agent comes to adopt a new outcome space gamma, in the sense of thinking that each outcome in it is a genuine possibility, then the standard coherence axioms make sense, right? That's going to be true. Sort of merely translated their beliefs onto some other outcome space that they don't necessarily endorse. What does coherence look like? Okay, I want to sort of make like one very important clarification about a restriction that I'm making here. I'm now sort of thinking that delta is finite. And the reason that I'm doing that is because then I can sort of exploit this cool fact that so on a finite space, right, if you accept all of the indicator gambles for like each outcome in the space, then by addition and scaling, you accept all of the positive gambles. So you could rewrite the standard coherence axioms where you just say, okay, they accept all of the indicators of each outcome in the space, and that would be the same. In the infinite setting, right, like this isn't true because we only have finite addition. So it's not true that just because you accept all of the indicators and so also all of the positive like scalings of them, right? If you have positive gambles that have infinite support, it's not necessarily true that you come to accept those just from that, right? So we would have to tweak the axioms a little bit more in the infinite case. So let's just do the finite case for now. So I'm going to say that a set of desirable gambles for some, finite delta is non-natively coherent if and only if it satisfies these axioms. So A1, A3, and A4 are just the same as D1, D3, and D4. But now our positivity axiom is different. So for all delta and delta, if they don't accept the indicator gamble for delta, then one of two things is true. So there are two valid reasons that an agent might not find the indicator of delta desirable. Either they don't think delta is a real possibility, and that's what the first clause says, right? It says, okay, if they don't accept this indicator of delta, then what had better be true is that what happens with respect to these things, right, just like actually doesn't matter to whether this gamble is desirable. So they actually just kind of ignore it. The other thing that could happen is that they could think that delta is like possible in the sense that, right, they think that there's this more general thing that they understand and they take sort of that possibility seriously. But like delta is a more specific way of making that thing true, right? So there's like two different, or however many different ways of making this more specific thing true. And they understand the more general thing, but they don't understand the more specific things. And so if that's what's going on, that's okay. But then they had better accept the indicator gamble for this more general thing. And it had also better be that they always treat all of these more specific things identically in the sense that we were talking about before, right? When we were talking about for gray, because we're sort of saying that actually they're just not distinguishing these. But that's also a sort of valid reason, right? That someone might not think that this more specific thing is desirable. Okay, so there are a couple of things to say about this. So one nice thing is that if we translate something that's sort of coherent on someone's native outcome space, then what's going to happen is so if we translate them to something that's like either expanded or refined or both, then they satisfy the non-native coherence axioms. So that's one nice direction. Also, right, so suppose that D satisfies the non-native coherence axioms. Then if we want to make them fully coherent, it's actually really easy. All we need to do is add in the weak dominators of gambles that they accept and the positive gambles, because otherwise, like they basically are coherent. The only way in which they aren't coherent is that. So yeah, when we translate an agent's beliefs onto a different outcome space, they won't typically be coherent in terms of the normal coherence axioms, but they will satisfy the non-native coherence axioms. And to be fully coherent, all they have to do is add in the positive gambles and weak dominators of gambles that they accept. We can also do the other direction. So if we have D expressed on some outcome space delta, and it satisfies the non-native coherence axioms, I can give you a recipe to construct a home space H and a set of desirable gambles B expressed on H, which is fully coherent. So on their home space, right, they satisfy the normal coherence axioms. And we can recover that from seeing that they're non-natively coherent on delta. So here's the recipe. First, we find the set of non-represented outcomes. So these are basically the things where they don't accept the indicators for them. And that's furthermore not because it's the kind of they accept like they treat something more general as a possibility, but not distinguishing the things. So these are the things where it's like actually they just literally don't sort of accept that these are possibilities. Then we sort of just take the outcome space where we just throw out all of those. And this thing I'm going to claim represents a possibly refined version of whatever their home space is. And so now what we need to do is just undo that refinement, right? We just sort of need to coarsen it into what they actually think is real. So basically, we just build equivalence classes of all of the outcomes that they treat identically. And then, right, if we take their outcome space as the set of those things, then that's by construction a coarsening of this R. And this is what I'm going to claim is their home space. And so one thing that we can see is if we, oh, sorry, here's what B is, right? So B is going to be sort of the gambles that when you cylindrically extend them to R, they're desirable according to D conditioned on R. And one thing that we can see is that the original set of gambles D that we started with is just the translation of this B that we've constructed to delta. Like so, cylindrically extending to R and then taking the possibility blind equivalent on delta. So what we have is that the non-native coherence axioms are both necessary and sufficient for coherent space when we're considering finite outcome spaces, right? So if someone is actually coherent on some space and we translate them, then they'll satisfy the non-native coherence axioms. If we have someone who satisfies the non-native coherence axioms on some space, then we can work out a home space on which they're fully coherent and what their gambles are on that space. Okay, here's a sort of maybe kind of minor, but I hope somewhat interesting connection with conditionalization, as we often think about it. So say that you have a set of desirable gambles D defined on delta and any event E consisting of a non-empty subset of delta. One normal way of defining conditionalization is that it's just the gambles defined on E, such that indicator of E F was in D. And I'm calling this eliminative conditioning, right? That's not a standard terminology. That's something that I'm saying. Because this is the case where we're restricting our outcome space. We're now not treating the things that are inconsistent with E as possible. But of course, another thing that people often define as a notion of conditioning is this like double bar version, where it's very similar, except you just say that it's the gambles defined on delta, where these called off versions were desirable before. And of course, as people will know, this is not typically coherent on delta, right? You're not taking like any of the positive gambles that are sort of positive only in virtue of the things that are in E complement. But of course, we can find the natural extension, and it turns out that the only thing that you need to do is actually add back the positive gambles. You might think that you would need to add back the weak dominators, but you don't, right? Because they're going to satisfy weak dominance on the sort of E part. And on the not E part, right, they accept like everything as long as like the E part is right. So actually, they already have all of the weak dominators of gambles that they accept in. What's missing is that they don't accept some of the positive gambles that are positive only on the E complement part. So eliminative conditioning represents a kind of pure contraction. You're again literally just throwing out some things that you thought were possible before. Now they just aren't possible. This, what I'm calling non-eliminative conditioning, is the translation of the eliminative version back to delta in exactly the way that I've been talking about before. So because it's pure contraction, it's actually just the possibility blind equivalent on delta. And the coherent version of non-eliminative conditioning, right, corresponds exactly to still treating all of the outcomes in delta as possible, even though you're treating things that are inconsistent with E as having probability 0. So this makes sense. This is exactly what you should do, right, when you sort of are thinking that these are things that still really might happen, right? I just think that they're, vanishingly unlikely. So that all makes perfect sense, and that's like a good reason, right, of why you should want to use one versus the other. And of course, right, we can see now, right, how you can sort of recover if you did the eliminative version, right, and you kind of wanted to get back to, well, no, actually, I do still think these things are possible. You can do that, right, in the way that I've described. Okay, so now finally, here's what I am saying I think an agent should do in these cases of awareness change. So I'm going to say that it should be a three-step process. First, they should translate their current beliefs to the new space. They should adopt the new space as a home, by which I mean become fully coherent, right? So just take the natural extension, which is just, again, going to be they just need to add back the weak dominators and they need to add in the positive gambles. And then, right, here's this like really general thing, right? They should just like consider any other evidence they have, like what their practical and epistemic risk preferences, sort of trade-offs between like how easy and hard it is to learn and like all of this kind of stuff, right? And, then they need to sort of decide like whether they should revise their beliefs. So you might think in Milo's case, right? Milo was treating the malfunction as like impossible before. And so now he can sort of treat it merely as possible. But you might still think, right, like, no, but that's crazy, right? Like treating it as probability 0 is still bizarre in that case. And that seems eminently sensible in a case like that. But like, is there sort of a general like mechanical thing to say about like what Milo should do? Like, no, right? There's no mechanical strategy for step 3. I don't think there's much of anything interesting to say here that's fully general. It's just like the agent has to think carefully about like what they think about risk and stuff now that they've sort of seen what they were believing before and what that really commits them to on this enlarged space. Um, but steps 1 and 2 are characterizable. And I'm arguing that this represents the minimal kind of revision which is necessary in cases of awareness change, right? So no matter what else is true, now that Milo does think that these are sort of genuine possibilities, he needs to do something coherent on this new space. And sort of absent very strong reasons to undermine his previous commitments, right? He might have been already making decisions on the basis of what he believed before. There's sort of going to be costs to changing those, right? This is kind of the minimal thing that he needs to do in order to become coherent now. But, it could very well be that he should do more, but I just don't think there's a way of saying in general what that should be. You kind of have to look at the details of the case. And one thing that's sort of frustrating about the awareness change literature and philosophy, the awareness growth literature, is people sort of like expect there to be a univocal answer about like how you should learn in these kinds of cases. And, I just sort of think like that's really weirdly unmotivated, right? It's going to be a really hard question, like in general, what you do in this last step. Okay. All right, so let me conclude with just saying a little bit more about some things that I have also thought about, or some things that I want to think about more, but that I didn't talk about in this talk. So here are some things that I've done a good amount of work on. So how to extend these ideas to like sets of desirable gamble sets. I've also thought a lot about connections with Wally's representation and variance principle. So what you want to do here is show that different translations marginalize to the same judgments for things that they can both express, right? So you kind of look at like, okay, what are the events that these different outcome spaces can both express? And when you marginalize two sets constructed of those events, then the point is going to be that these should be the same. And that's going to be true for my translation scheme. Something I'm very interested in, but seems really hard, is the stuff that I was talking about before. So, how far can we push translations? So, can we say interesting and sensible things about cases, right, where neither outcome space is actually more informative than the other? So, they just kind of like overlap in interesting ways. I'm really not sure what to say about this kind of thing. I have tried to think about it a bit. It seems really difficult, but it does seem super interesting and important. And finally, something that I haven't thought that much about. I mean, I can sketch like a little bit, like how I think it would go, but is clearly important, which is extending these results to infinite outcome spaces. So my really sort of brief sketch, which again, I haven't thought about super carefully, so, apologies if this doesn't make sense. But I think the simplest tweak is just going to be to kind of have weak dominance as a separate constraint. So in your axioms, you would just have like, okay, so you accept the indicators, right? Like, and you can kind of have exceptions for why you accept the indicators. And then separately, you also say that when you accept a gamble, you accept every gamble that weakly dominates it. And I think that will get us the kind of positivity that we want in that kind of case. But again, apologies, I haven't thought about this super carefully. Okay, so that's the end of the talk. Very special thanks to my friends and colleagues Arthur, Katrin Campbell-Moore, and Jason Connick. So, back when I was thinking about all of this, I had a lot of great conversations with all three of them, and they had a lot of very useful insights. So Katrin was actually also working on kind of, coming up with coherence axioms for these awareness change kind of things at the same time. And also this kind of insight about like using indicators of an event to sort of test for possibility is something that Jason and I have talked quite a lot about. Arthur pushed me on a lot of things that actually I sort of didn't talk about here in the talk, but there's sort of questions about like, what do you say sort of about translating between people when they disagree positively about what the outcome space is? So it's not that like one is ignorant, right? It's that someone says, I think these more fine-grained possibilities are possible. And someone else thinks, no, I think that this combined thing is something we can kind of empirically verify, but I don't think there's any fact about which one of these more fine-grained things that you're saying can happen. And that's really interesting and a bit different from some of the things that I've said there. Um, so yeah, thank you all very much for listening to my talk and for any questions that you have. Thank you very much.